So our first speaker in this session is Šoda from the Perimeter Institute.
Thank you. Today I'll tell you about the framework, this time done in collaboration with Unruh, who's here, and Šoda at MIT. I'm going to tell you about two effects in acceleration-induced light matter interaction. Stimulated Unruh effect and acceleration-induced transparency. So let's start with acceleration. I think we could all agree that acceleration doesn't fit naturally into quantum physics. There's one effect where we understand it well, which is the Unruh effect. But we all know that it's a very small effect, so it's hard to measure. So you might wonder, are there any more effects? And the reason why that might be an important question is that acceleration is related to gravity via the equivalence principle. So understanding acceleration-induced effects better would allow us to understand better gravity and quantum physics at the same time. And in this talk today, I will tell you about new acceleration-induced phenomena, which will lead to increased measurability of the Unruh effect, and it will give us new insights into acceleration and therefore also gravity. When it comes to light-matter interactions, for this talk today, it's important to understand the difference between resonant and non-resonant interactions. The resonant ones are the usual ones, absorption and emission. They are responsible for the fact that we can see and the way that we see the world around us, so they are everywhere around us. They are strong interaction terms, which is why they are the usual ones. And it's well known that these kind of interaction terms can be stimulated, and it's done in labs, for example, using lasers. On the other hand, we have non-resonant interaction terms. They are unusual. Unruh effect and Hawking effect are in this category, and they are weak, which is, of course, why they are unusual. And these interaction terms have to be activated, actually, by either acceleration or gravity. So this is what's already known about light-matter interactions. And today, the new things I'm going to present is that on the resonant side, we find that the resonant interaction terms can be modulated with acceleration or gravity. So this will lead to a new phenomenon of acceleration-induced transparency. And on the other hand, for the non-resonant terms, we find that they too can be stimulated. Remember, resonant terms, we already know, they're usually stimulated in the lab. But now the non-resonant terms are also stimulated, which makes them stronger and more easily measurable. Okay, so this is the story. As I just said, we know that the resonant terms can be stimulated. Now we find that also the non-resonant terms can be stimulated as well. Think of Unruh effect, Hawking effect. So what we do, we first stimulate the Unruh effect. We do this by presence of photons in the quantum field. The problem that we encounter is the usual one, which is stimulating the non-resonant terms also, of course, stimulates the resonant terms, because they all come from the same Hamiltonian. But we didn't give up then. We found a solution to this problem, which was this new phenomenon of acceleration-induced transparency, which suppresses the resonant terms to zero. So the outcome is that we are left with only strong non-resonant terms, and in particular a strong Unruh effect. Okay, so that was in words, and now we get into the mathematical description of it. It's actually very easy. It's the standard setup of Unruh detector, which is a two-level quantum system with an energy gap omega. And we have a scalar quantum field, just your standard scalar quantum field. And the interaction Hamiltonian has the sigma x, or the flipping operator for the detector. And it interacts with the quantum field along its trajectory, so along the trajectory of the Unruh detector. So that's the trajectory. And if you look at the interaction Hamiltonian more closely, we can see that the interaction terms break up into two different categories that are talked about, the resonant terms and non-resonant terms. The resonant ones are, they do the following. They either excite the detector while de-exciting the field, or the other way around. And the non-resonant terms either excite both of them at the same time or de-excite both of them at the same time. And in the standard Unruh effect, what we do is compute the amplitude for this kind of transition, where we start out in the ground state of the detector and the vacuum state of the field, and we want to know what the amplitude is for the detector becoming excited. We don't care so much about what happens to the field, so we only care about exciting the detector while starting out in the ground state of both the detector and the field. So let's compute this amplitude in first order perturbation theory. We find an expression like this. This is the coupling constant G from here. This is some normalization, it's not so important. The most important part is this time integral I plus, the formula you can find here. What I plus is some kind of a Fourier transform of the phase function that comes from the trajectory. So you can think of it this way. And it will be an important part of this presentation. Now, let's move on to the stimulated Unruh effect. The setup is the same as before, with one crucial difference, which is that the field starts out in an excited state instead of the vacuum state. Here I'll work with the Fock states, but that's not super important. So the field starts out in an excited state, and we calculate the transition from this initial state to whichever outgoing state the interaction Hamiltonian produces. And this is the result. Most notably, this is the Unruh term. You see that it still has the time integral I plus, but importantly, it has the square root of n plus 1, which is the enhancement of the Unruh effect. And also we have this other term, which comes from the resonant interaction. So we're happy about having stimulated the Unruh term, and we're not so happy about this one. We're going to have to get rid of it somehow. Just a quick comparison. Whereas we started in the ground state of the detector and the field for the standard Unruh effect, here in the stimulated effect, we start out in an excited state of the field, which then affects the probability for the Unruh effect to happen. Namely, the probability for the Unruh effect gets enhanced by n, where n is the number of photons in the field. Okay, and just I mentioned that Fock state is not important, so here I just show it. If you do a similar computation for coherent state or a thermal state, you get again enhancement by the expected number of photons in the field. Okay, so we just saw we can stimulate the Unruh effect, that's great, but we got this nuisance term that comes from the resonant interactions. And that's boring because we see it all the time, so we want to get rid of it. And the insight into how to get rid of the resonant term contribution comes from these I minus plus time integrals. So we know how to eliminate the I plus time integral. In inertial motion, it's equal to 0. We all know this fact. Basically, you cannot have Unruh effect if the detector is moving in inertial motion, which is why Unruh effect is an effect that comes with accelerated trajectories. So you need an accelerated trajectory in order to have this be non-zero. So this is the non-resonant time integral. In inertial motion, however, we know that resonant integrals are non-zero. That's why resonant terms are ubiquitous. They're everywhere around us. So typically, we are thinking of how to turn on the Unruh effect by changing something about this time integral. But here, we're going to change the perspective and try to get rid of this one. So this one is typically non-zero, and we're going to try to get rid of it. And we can get rid of it. For that, we'll show that there are some trajectories which kill off the resonant time integral. They set it to 0, while the non-resonant time integral is non-zero. And the reason why that happens is that acceleration impacts not only non-resonant terms, but also the resonant terms. And that leads us to acceleration-induced transparency. So typically we think of acceleration only impacting non-resonant terms, Unruh effect, Hawking effect, but here it's kind of flipped upside down and we're thinking of it impacting resonant interactions. Okay, and so what this phenomenon of acceleration-induced transparency will do is cross off the resonant contribution and we'll be left with a clean, strong Unruh effect. What's left to show is how that works. Well, let's see the simplest toy model of acceleration-induced transparency. In this toy model, we choose the trajectory for the Unruh detector to be 3 different inertial motions at 3 different velocities. And the question, what we have to show here is that we can tune this trajectory such that this integral is equal to 0. And after some calculations, we don't have to go through them, you can show that indeed you can choose the parameters of this trajectory to be such that this integral goes to 0. And so the conclusion here is, if you choose an Unruh detector with a gap omega, the energy gap omega, and it moves at this trajectory, it will not get excited due to resonant terms. At the same time, the I plus integral is non-zero. So if in an experiment we find that the detector is excited, we know that it's due to the non-resonant terms. So only the Unruh effect type of terms will contribute to the excitation of the detector. And this is the plot that shows this phenomenon. So that's the absolute value of the I minus integral, something like an absorption curve for resonant interactions. You see 2 peaks, 2 resonant peaks, but in between them we get this point where the I minus integral goes exactly to 0. So that's where that's when the resonant terms don't contribute at all. And when we zoom into this point, we can see that indeed it goes to 0, while at the same time the blue curve shows you the I plus integral, the Unruh effect integral, and that one is non-zero. So that tells you that if you do the experiment with these parameters, you'll find that if the detector gets excited, it's only due to Unruh effect interaction terms. Just also to mention, what I showed you was a toy model, and it had these abrupt changes of velocity, but we wanted to make sure that nothing non-physical is happening here, so we smoothed out the trajectory, and we found basically the same thing. So we found that we can also suppress the resonant terms to be as small as you want. So summary so far, we are nearly at the end of the talk. We found that we can stimulate not only resonant interactions, but also the non-resonant ones. We found that this was a problem because then also the resonant terms were contributing, and they are still too strong, so they would be suppressing the Unruh type transitions. But then we solved this problem using acceleration-induced transparency, and what we are left with is dominant non-resonant terms, meaning a strong Unruh effect, which is a suggestion for a new method to measure the Unruh effect in the lab. And finally, before I finish the talk, one more interesting thing we found was the catalyzed Unruh effect. This is a type of Unruh effect where the field serves as a catalyst for the excitation of the detector. What I mean by that is that the detector gets excited from the ground state to the excited state, while the field stays in the same state, in the same coherent state. So it only serves as a catalyst. And we wondered, is this effect exotic? How often does it happen? So in order to quantify that, we had to divide the probability of the catalyzed Unruh effect with the probability of the total Unruh effect. We have these formulas. And it turns out that when you include acceleration-induced transparency, that means you kill off the I- contributions, you get this kind of ratio. So with acceleration-induced transparency, catalyzed Unruh effect is super dominant when number of photons is large in the field. So that's a curiosity. And to summarize my talk, I showed you new effects in acceleration-induced phenomena in light matter interactions, stimulated Unruh effect, acceleration-induced transparency, and the catalyzed Unruh effect. I showed how combining them leads us to an improved measurability of the Unruh effect, showed it in this schematic formula, as stimulated Unruh is n times standard Unruh. And that's an interesting formula, because if you look at this number n, and you look at how large this n can typically be, well, n can be very large. For example, we calculated for this example 10 to the 16. So in principle, you can make the Unruh effect much more measurable than you used to be able to. So for the outlook, this suggests new directions of research, also for gravity. So first of all, I talked about acceleration-induced transparency, and we know the relationship between gravity and acceleration. So this suggests studies into gravity-induced translucency or even full transparency. And also, we showed that we can stimulate the Unruh effect, and the Unruh effect is very similar to the Hawking effect. So maybe we can also stimulate the Hawking effect, for example, by particles that can be found on the accretion disks. So you basically need the presence of photons in order to stimulate these non-resonant effects, and maybe that also happens near black holes, but that's left to be investigated. Thank you very much.
Only 3 minutes for questions. Okay, let's start. I think you first.
Yes. For an optician, you said a little bit of strange things, that non-resonant effects are weak. So the reflection on the mirror is a fully non-resonant effect, and it is not weak at all. Okay? And then that acceleration are difficult to manage, but you just make oscillations. Oscillations are acceleration. And so you just oscillate a mirror, and then you get the equivalent of the Unruh effect, that is basically scattering from a moving object. And so this is called squeezing, and you produce vacuum squeeze states. So vacuum squeeze state has a pretty good equivalent of the Unruh effect, except that it's not uniform acceleration, it's oscillation, but it works exactly the same, and it has been done 30 years ago. I did it, by the way.
Okay, so what I actually said was that acceleration doesn't fit naturally into the framework, but what you're saying is like should have also included squeezing of states in the list of acceleration-induced effects. Okay. Yeah.
Yes, so this is well known in optics. So I don't know whether you are aware of that or not.
Yeah, I'm talking about light matter interactions. But I mean, you would agree that acceleration-induced transparency, for example, we worked with an optician, quantum optics.
Yes, what you say is correct, but what I say that they are much easier to implement equivalent of Unruh acceleration, which is just to oscillate a mirror. So you don't oscillate the mirror because you cannot move it at optical frequency. So what you put is a transparent medium, and you modulate the refractive index at optical frequency. And this produces squeeze lag. That is, you get photon from the vacuum, and it's a vacuum squeeze lag.
Yeah,
but it has been done for 30 years.
The dynamic Casimir effect is not. Look, I have a question. It's related.
It's just another effect.
Yes, so, but since she didn't speak about at all, okay.
Fair enough, that's another effect.
Yeah, she spoke about something else.
The question is,
I thought that extremely interesting, but can you tell me, with what precision does this accelerative path have to be traced out before you get the cancellation? And what sort of coarse graining could you introduce there and still have the cancellation?
Okay, that depends on, of course, on your experimental capabilities. So, of course, you will never hit exactly zero. This is what you're asking, right? You will never hit exactly zero. You'll be in some neighborhood of the zero. It all depends on, you want the non-resonant transitions to be larger than the non-resonant ones, so maybe 1 factor of 10, and that's how precise you have to be in doing a trajectory to have stronger non-resonant than resonant effects. So you can see it in this plot.
Right, so there is some region there where one could have an accelerating detector that could satisfy this concept.
And it requires some fine-tuning. Yeah.
Okay, time is over, so we have only one more question.
Thank you for the very lovely talk. In what sense is it time reversed? And is there an issue about the length of the world line of the detector? Because in the more mathematical literature, there's much discussion of the UDW detector having to last a long time.
Right. Okay. I wrote on some slide that it's time reversed Unruh effect is nothing too fancy. It's just instead of having both the field and the detector excited at the same time, the time reversed is just the opposite of that. So it's nothing fancy. You can see it in the interaction Hamiltonian. For the other question, that's a good question. I think then you would just have to modify. You would use the same principles, but you'd have to modify it. Just a sec. You have to modify the boundaries here, right?
Yeah.
But I think you can probably achieve the same phenomena. Only you'd have to, not integrate from minus infinity to plus infinity, but some finite time intervals. And I suppose you can achieve the same effects.
Okay, great. Let's thank Barbara again.